Thanks, Ketan. So this talk is about a new feature in MFEM. It's sort of my dream going to be through, and so it's deterministic transport MFEM in the app, and the actual use of the deterministic transport should serve to advance fidelity of fusion energy simulations, and it's work of the GSN team. Oops. I'll skip abstract. So the GSN team's here. I guess probably everyone knows Veselin. Many people will know Jan. Some people should know Terry. People maybe know me. I don't know. And we also people. Sorry. And we also have on board Alex Mode and Colby Frank. So. New blood and guys who are actually extending our focus in brand new directions, and for me personally, there should be a lot of potential. So let's see what's this talk about. First, motivation. So fusion energy probably. So hopefully in the 40s, at the latest in the 50s, we should have energy from fusion, like electricity from fusion. And last year in December, it was the breakthrough because for the first time, we were able to extract more energy from the target than we invested to trigger the reaction. And so in numbers, it's called fusion ignition. In reality, the fusion ignition actually happened in August 8th, 2021. But this was officially the breakthrough that we made the more energy out than in, and so the yield was 3.15 megajoules. However, maybe you don't know, recently we had a new record. So on July 30th, on Sunday, there was a yield of 3.88 megajoule, which is Q almost 2. But what's interesting is that the difference between 210808, we had 1.96 megajoules of laser and 1.3 megajoules out. We upgraded the laser by 8% roughly, but we tripled the gain in July 30th. So you can see it's really non-linear. And I will spoil a little that there is an upcoming shot. I cannot tell when exactly, but soonish. And we got an upgrade of the lasers. So it's not 2.05, now it's 2.2 megajoules. So it's addition of, again, like 8%. And so if we do the math, it might be tripled. And so you might have, 10 megajoules outcome. So yeah, we will hear soon. And just to stay positive, from the breakthrough, every repeat of the ICF experiment from December 5th, 2022, always the gain was more than 1. You just don't hear about the gains, which is like 1.1, because what's the point if we have 1.9 now? But every repeat was more than 1, and this is really great news. Now the truth, what's going on under the hood. So on the right, you can see the graphic, what's going on. So there is the capsule. It looks like a sun because it actually triggers the conditions very similar to sun. And in the best shot, we burned roughly 5% of the fuel in the capsule. And so there is obviously a space to improve the portion of fuel to be burned. And the question is how to do it. And we work very hard to improve our simulations. And it goes a little beyond the traditional accuracy or the fastest or the best numerical methods. We actually want to change the model. We want to go from fluid description to chip in the important information which happens on the particle level. And the right word for this is to include kinetics. And it's actually what Sunichi gave a talk about. So it's very similar. And if we can get the information from the kinetics, we might get much more than 5% of the fuel to be burned. So now what it means, sort of the kinetics. So in regular world, we would use three-dimensional discretizations, and we would evolve our fields in time. And there is the whole finite element exterior calculus, the RAM complex, and it's really cool, but usually it's considered in 3D. If you want to include the physics, which is on the microscopic level. Sorry, Siri picked up. So we need to add dimensions to describe particles. We want to describe particles' directionality and their velocity or energy. And so here in the scheme, you can see it adds dimensions in directionality. It's two angles. It's like a sphere, and one dimension in energy, and we will keep time. And so what we want to get this into MFEM, and we want to make it as compatible with existing features as we can. And so it means we use Lagrangian meshes for up to 3D as we do now, but we want to add those new dimensions. And the step forward from the existing methods is we want to do the dimensions in finite element method flavor. So high order with meshes, with all the cool features we developed in 3D. And because it's important to say also, if you go to 7 dimensions, suddenly memory is a serious issue, because just having DOFs, it's hard. If you want to store things for 7 dimensions, you're screwed. And so we want to do it matrix free, and we actually introduce like a novel deterministic transport model method called GSM, and there we also believe for a significant cutoff in the number of DOFs. But first, let me explain where we are right now. So on the left in space, you can see this is meshes we would regularly use. And we are adding the angular meshes and energy meshes. And so the idea is to make it abstract enough so that user has actually options to use what the user wants. And so we build it in terms of product of meshes. So if you, for example, have the meshes if you have one mesh in column 1, one mesh in column 2, the sphere, and one mesh in column 3, the energy, those meshes are MFEM. We have the technology to make them their product, and we have the technology of DG working on this multidimensional space. And to spoil a little, the implementation is actually very general. So this pretty much we talk about 6D because this is like the state of the art of phase space. But what we did with the implementation, we can do n-dimensional things. So if you have n meshes of different dimensions, you can product them and you can run, I don't know, 2n-dimensional simulation if you want to. So this is something which is going to MFEM. And I would like to show you what it looks like from the user perspective. So I consider myself here a user because Jan is actually doing the work of implementations and discussions about design, but I'm not doing the under the hood work. I actually test the code as well. And so simply we have this equation. So it's a time evolving transport of Crookes type, which means there is advection. This one is n-dimensional. There is some advection field A with n components. And we have absorption. So it's the sigma minus sigma psi on the right-hand side. And we have a source, which is sigma B. This particular notation corresponds to radiation transport, but it's Crookes type. And so what it is, we can do n-dimensional mesh. We can do very simply define n-dimensional advection field, where this is where the devil's hidden. And we can directly use MFEM solvers, time integrators, visualization. And then going forward, it's based on generic programming abstraction, we believe, and we have some results that it is performant. It is matrix free. The only memory we occupy is for DOFs. If we include also DOFs of the mesh. And so, yeah, it's GPU portable. And the thing you see on the right-hand side, it's a snippet of the code, which actually works. And it's 49 lines, and it defines a 6D problem. And before having this code in hand, it took me like years to do something similar. And here I was able in 15 minutes define polar SN in 3D, and you will actually see what it means, polar SN, for our purposes. And so in principle, I could stop here. This is what we have, and this is like the cool new feature for AMFN. But let me tell you a little more about that's how we want to use it. It's for the application is to have it for fusion to simulate and predict fusion experiments. And so the difficulty is it is a 6D problem if you want to include kinetics in our nowadays rad hydro simulations. So on the left, it's the typical ICF all-around. The red dotted lines sort of say what would be the propagation of energy. And so if you focus around the capsule, this should be spherically symmetric. So we would expect that the flow is radial and goes directly in direction to the center of the capsule. And if we achieve this in the experimental, in the all-around, we have the best conditions to compress the capsule. And so the capsule, when it starts, it's 1 millimeter in diameter. No, sorry, it's 2 millimeters in diameter, 1 millimeter in radial. And it is 30 times shrank in radius, which means 10,000 times smaller in volume. And so just imagine how small it gets. And so if you do any errors in terms of compressing non-spherically, non-symmetrically, you are not going to, the final product is not going to be a spherical capsule. It is going to be something, like we have here, bottom left figure. And even worse, it's not just it's compressed not perfectly symmetrically, but it makes the distribution of material inside at the center of the capsule, where this is where the nuclear reaction is actually triggered. So it's mixed from different materials, and it's so difficult to control. And so that's why we are obsessed about the spherical symmetry, about the radiation drive needs to be spherically symmetric as much as possible. And if you now, this is continuous. If you go discrete, you introduce mesh, you introduce discretization, and just imagine how sensitive needs to be your discretization so it doesn't seed any numerical instabilities and non-symmetry of the compressed capsule. And so this is actually achieved by a concept called polar SN. And just very quickly, it's something similar to rotating angular coordinates. So in our 6D, we don't have the coordinate system for directions of particles to be fixed, but it actually rotates in space. Like if you move to different positions, it actually tries to rotate the sphere of the description of particles in some smart way. And for all around, it's very obvious you want to point it directly to the center of the capsule. However, if we go to the tokamaks, it's again extremely complicated geometry, even though it's a donut. Because once you have the movement of the particles around the magnetic fields, they do like really weird trajectories. And so again, if you know how they flow the energy, so it has some directionality, and this is not going to be like perfect. It doesn't look like the donut anymore. And so again, we introduce our transformation with the R is the rotation matrix, which varies in space, and we can actually follow these lines. And so this would be actually very close, like a way how to introduce kinetics in the model of Sunichi. And so this is a little visualization what it means. Like if we have the transformation, the important part again always is the Jacobian. So I'll call it J. So if we have the Jacobian of the transformation, we can introduce the polar SN, which on the right you can see gray and white cells. I hope you see the difference. So gray cells, the two-dimensional sphere of directions of the particles is fixed. So it's whenever you sit at the spatial point, it doesn't change the orientation of the z-axis. If we look at the white cells, it's the application of the R matrix in the sense that it rotates the sphere always to the origin, and we get an amazing result, because if we use gray cells, we get the pattern, the flower pattern in a perfect all-around case. So the the simulation we see here, it's called perfect all-around because it's perfectly symmetric. And so in continuous problem, there should be no non-radial dependence. But the flower obviously gives you a lot of, it's weird. But if we use the polar SN, the white cells pointing to the center, we get perfect symmetry. And not only by eyeball, if we check up the accuracy of the solution, it is perfectly symmetric. And it's actually the only way how we run the simulations, so we can understand the capsules. So if we don't have polar SN, we cannot run deterministic transport and accurate things. I will go quickly over this slide, but the rotation of the angular system actually introduces like a more flavor into the advection in phase space. So traditional radiation transport advects only in XYZ, if I say so, in spatial dimensions. If we start to rotate things, so if the R matrix is not identity, we actually start to advect also in other dimensions of the phase space, so in angles. And there is actually also the energy dimension, and it can be also used to advect the distribution function in the energy dimension. And here, it's a visualization of a special concept that we can actually make the energy dimension to feel as a Lagrangian. And so it stretches and compresses similarly to the mass of fluid. Here we only talk about energy, and actually we stretch it around the mean energy given by temperature. And we already saw some cool results. So it increases the accuracy of the method and saves the degrees of freedom you need to invest to describe your energy of the particles. And to summarize, the concept for ICF and tokamaks we would call flux GSN, because we care about how we transport energy in the device, like what's the directionality of the transport or flux of energy. And we can achieve this by introducing the rotation matrix. We can also do the scaling of energy. And so the equation here, it's actually not an equation, it's just the definition what the advection field looks like. So you as a user from the outside define, okay, so I want to have the rotation of my system this way. And we have the methodology how to introduce this as advection vector in 6D, let's say. And you can just implement the code on 50 lines as I did before. I mean, it would be more here. It's more complicated advection field, but we use tensor analysis, tensor calculus to have the things generally interpreted. There is another concept, we call it fluid GSN, and the transport, it's of particles, but you always care about the background. So for us, it would be fluid. So for example, we have photons moving in plasma. So plasma is fluid on the background. And I'm sure you know again, I don't remember the effect. So it's redshift. Okay. No,
Doppler?
Doppler, yes, thanks. Yes, this is amazing. So the once you have moving background, it's actually very similar to if the particles are moving with respect to you. So there would be like transformation, but the moving background creates a Doppler effect. And so the fluid GSN helps you. So this is a particular model for a relativistic radiation transport, and it tells you how you want to advect your function, your radiation intensity psi. And there is terms that pop up because of the fluid motion in the background, and it's actually given by the gradient of the bulk velocity. And so once you have gradient of bulk velocity, you start to see things like aberration and Doppler effect. So shift in energy, shift in angle. And so again, with our code, it's literally trivial to set up this kind of problem. It's, I mean, for me, it's impressive. And great job, Jan. And almost done. it's great to have high order discretizations, but it's still discrete world versus continuous. And we know in continuous world, there is things that simply hold, and we call it non-negotiable physics. And it's not trivial to get it right. And so, for example, we definitely need our discretization to be energy conservative. We would like to have that it maintains the positivity. It has a diffusion limit. This is very specific to radiation transport. We would like to also maintain symmetry. If our definition of the problem is symmetric, then the solution also should be symmetric. And so, without explaining how we are actually able to achieve all these things at once, which I believe it's very special for deterministic transport discretization in n dimensions, because everything I'm describing here works in n dimensions. And yeah, okay. I'm a little tired to explain perfectly this example, but this is the 49 lines I showed before. It's actually here described. So the point is, it's 3 dimensions in space. It's a spherical mesh. So it's a rho, theta, and phi. It has 2 angles. So it has the nice description of the directionality, mu, little omega. And I just use piecewise constant energy. So it's actually 5D gray transport. But I still defined the advection fields to be 6-dimensional. These formulas simply come from the correct orientation of your rotation matrix to the origin. So you can do it analytically, and this is what you get. And we test it in the perfect all-around. So it's schematically here. The red line is the outside surface. There we have homogeneous isotropic radiation inflow. And the blue ring is the capsule, which is a pure absorbent. So no radiation makes it inside. And so what happens if you look at the left? So there is radiation at the boundary. It goes inside, but it's shaded by the capsule. So that's why it decays. And when it hits the wall, it goes to 0. I mean, it should. It does not in the traditional method like diamond difference. So there is the overshoot is just really too much. And so the figure on the right tells you what it looks like with our example. So it's the same spatial profile. The difference is that, for example, the minimum value is -2 point, but it's 10 to the -20. So it's just a solver tolerance. So this demonstrates the positivity. And it's actually running fully 6D and recovers 1D solution spherically symmetric. Okay, conclusions and future work. So we brought n-dimensional feature to MFEM. Now it's internally, the goal is to make it public. So we will see how the timeline goes. It uses MFEM traditional features as mesh, solvers, time integrators, visualization. It's based on generic programming abstraction with templates, and it's matrix-free. More to come is the code is fairly general, so we are going to include diffusion in n dimensions. So it's going to be advection diffusion solver. We are also going to provide feature to integrate over the momentum dimensions, so we can set up integral differential equations, also nonlinear. And the last one, adaptive mesh refinement in n dimension. This is like a dream, but yeah, we need to dream big. On the right, it's just recall back to Alex Modi's presentation and also work of Colby. So if you look up, I would focus on the B middle figure. It's very, very good match to heat flux in fusion plasma relevant conditions. And the accuracy is amazing. It's a non-local conditions. And as Alex said, the cost of operations is like it's like 1 million times faster. And because this is, I really like working for MFEM and I like the international flavor. So I wanted to share with you something that happened to me very often, and I believe that because we had more than 50% of speakers non-native, and the 50% of workshop participants are non-native, or they don't, English is not their native language. So I believe you would relate that sometimes there is a difference between how the talk looks like and how the author is actually smart. So, and yes, that's it.
It's a good thing we all speak math, right?
Yes.
Exactly, correct.
That was great, man. It's good to see support for n-dimensional meshes and MFEM. I think we have time for a question or two.
Yeah, okay. So, great presentation. First of all, my usual question maybe, what you presented only considered like analytically given direction of preference or the discretization in the angular dimensions. So how about some adaptivity? Because maybe even in that whole realm, there might be some physical asymmetry, and when you are assuming that full symmetry, then you are actually suppressing it somehow artificially or something like that. So how about some adaptive methods or some local definitions of the direction of preference?
Thanks for the question. Really good question. So that's exactly right. The current state only allows for analytical prescriptions of the rotation matrix or that advection field. The next step is to make it general, and so in simple description is that the rotation matrix, it will be actually dependent on other fields, or maybe the field itself, like make it nonlinear. And so it means we can provide the rotation as we need to, or as we believe is the best locally. The feature is not there yet. It requires some coupling with grid functions or touch the DOFs and also integrate over the dimensions. But it's definitely, so in the future plan, I think it was the point number 1 or point number 2, point number 2, the integral differential equations. It goes very similar to what you said. Thanks, good question.
Okay, thanks.
Okay.
There's another question, I think.
Yeah, she had a question. I think she had a question, yeah. She, you want to chime in?
Can you hear me?
Yep.
Oh, yeah, sorry, I wasn't sure. How do you do load balancing with this high dimensional space?
Yes. So right now it's not parallel. So
Really? Wow, that's impressive.
I mean, sorry. So it's not parallelized. So we do not load balance.
Okay.
The thing is, again, the abstraction is done in the way. So it's a modular thing, and the load balancing would be happening. So we believe to put the load on the MFEM team.
Okay, sounds good.
But again, it's another very good question. So what the things we would be doing right now, or what we can do right now is we would be parallelizing only on the spatial mesh, and so we wouldn't be cutting into pieces the additional dimensions.
Yeah. Thanks.
Thank you.
Very interesting.